Why ice cream transport is closer to cryogenics than to food delivery. Inside a warehouse kept colder than the Arctic night, pallets of ice cream wait in silence. No steam, no urgency, just precision. Outside, a refrigerated trailer idles, its internal sensors scanning the environment down to the 10th of a degree. This isn't just about keeping products cold. This is the choreography of cryogenics, applied not to medicine, not to spacecraft, but to something as familiar as dessert. Ice cream, for all its playful reputation, is one of the most thermally fragile substances in the entire cold chain. Between factory and freezer, it walks a tightrope suspended over irreversible loss. A single deviation of just 2 degrees Celsius above -20, and it begins to change. Microscopic ice crystals form inside its structure, shifting texture, breaking down emulsions, releasing air pockets. What was once creamy and smooth becomes coarse, watery, unpredictable. You can't see the damage, but you can taste it. In many ways, transporting ice cream resembles transporting semiconductor chips. Both are sensitive to the invisible, to minor vibrations, to shifts in pressure, to thermal shock. Just like a dust particle can ruin $1 million microchip, a 5-second exposure to ambient air can destroy the structural memory of a frozen dessert. These aren't coincidences. They're symptoms of the same demand. Precision, cryogenic-grade insulation, isn't optional. It's engineered. Inside the containers, eutectic plates line the walls, devices that freeze solid and hold sub-zero temperatures for hours without fluctuation. Some systems use phase change materials, substances designed to absorb or release thermal energy while maintaining a constant internal temperature. They don't just keep it cold. They stabilize the very climate around the product, acting like thermal shock absorbers in the frozen logistics ecosystem. It's easy to think of cold chain transport as something new, but its foundations lie in military engineering. During World War II, naval vessels developed sealed refrigeration compartments to carry meat across entire oceans. Those principles, sealed air loops, controlled thaw zones, layered thermal buffers, were the basis for today's refrigerated intermodal containers. The same industrial-grade technology now ensures that a tub of vanilla, made in Wisconsin, can arrive in Texas without losing a fraction of its integrity. This isn't food transport, it's controlled environmental migration. Every unit moved, every second in transit is a small battle against entropy. And yet, temperature is only part of the equation, because the true challenge isn't just in maintaining the cold, it's in never allowing it to falter. Not once, not for a moment. And in that relentless quest, the most dangerous moment isn't when the product leaves the freezer. It's when the trailer door opens. Even the most advanced refrigeration system can be undone by a single open door. In theory, the cold chain is a sealed continuum, from production to delivery, an unbroken line of sub-zero conditions. But in reality, there are invisible gaps. One of the most critical, thermal lag during cross-docking. It's a quiet moment, easily overlooked. A pallet arrives at a logistics hub. The truck doors open. For a few minutes, 3, sometimes 5, the container breathes in the ambient air. The loading crew works quickly, but the damage has already begun. Ice cream, perfectly frozen at -20, begins to absorb heat from the surrounding environment. Not on the surface, at the core. A rise of just a few degrees may seem trivial, but inside, the ice cream is shifting. Microcrystals begin to enlarge. Texture begins to change. Air cells begin to collapse. The thermal lag becomes irreversible decay. It's a paradox of modern logistics. Millions invested in refrigeration systems, sensor arrays, and container insulation, all compromised by what happens in the human interface. The handoff, the pause, the open door. To counter this, engineers have developed active airflow barriers. Systems that generate pressurized cold air curtains the moment a container is accessed. But barriers alone are not enough. Predictive algorithms now calculate the exact time needed for safe unloading adjusting airflow and fan velocity based on product sensitivity, ambient humidity, and remaining cold reserves. This is no longer just logistics. It's thermal choreography. Every movement must be timed, every opening calculated. The science is clear. In a controlled study simulating common cross-docking conditions, a 3-minute exposure caused the core temperature of an ice cream pallet to rise by 4.5 degrees Celsius. The product never fully recovered. The outer layers refroze, but the internal structure remained fractured, texture lost, air content destabilized, flavor compromised. In practice, this isn't theoretical. In 2022, a major distribution center in the US, Midwest faced a sudden recall of over $600,000 in frozen goods. The cause? A series of layovers during a holiday weekend where transfer times exceeded protocol. The result? Partial thawing, unnoticed by the eye, but devastating to product quality. A logistical oversight with industrial-scale consequences. This raises a fundamental question. If so much effort is dedicated to building and maintaining the cold chain, from custom trailers to smart sensors to eutectic insulation, why allow the weak point to be the interface between systems? Why invest in state-of-the-art refrigeration if the critical failure comes when people transfer the load? The answer lies not only in design, but in culture. Until recently, thermal discipline was viewed as a temperature issue, measured in degrees, solved with insulation. But what's emerging is something far more complex. A realization that temperature is not static. It moves, it lingers, it reacts. And above all, it accumulates across time and space. Every second exposed, every door opened, is a variable that must be managed with precision. The future of frozen transport depends on it. Because no matter how perfect the production, how robust the container, or how cold the freezer, one vulnerable moment during transit can melt it all. Freezing isn't enough. Why the cold chain fails without kinetic control? Ice cream doesn't just melt from heat. It can degrade in silence, still frozen, while in motion. It happens inside the container, during transport, when pallets sway, when vibrations ripple through the structure of the load. The industry has long treated frozen cargo as static, as if temperature alone guaranteed preservation. But the reality is more complex. The cargo is in motion, and so is the ice cream inside it. Every bump in the road, every turn, every sudden break translates into kinetic stress. The impact is microscopic, but relentless. Vibrations disturb the emulsion. Air bubbles expand and collapse. Over time, this movement alters the microstructure, introducing voids, weakening the cream matrix, and triggering crystallization at points of structural fatigue. The solution didn't come from food logistics. It came from naval engineering. Gyroscopic stabilizers, originally developed to balance ships in open water, are now being adapted to secure pallets of frozen goods. These kinetic dampening systems, integrated into the floor of reefer trailers, reduce vertical jostling by distributing motion across a counterbalanced axis. It's a quiet technology. There are no moving arms or robotic arms, just calibrated stability. And its effect is profound. Tests conducted by a dairy consortium in Brazil showed a 17% reduction in void crystallization in shipments that used vibration-absorbing pallets. The ice cream arrived with smoother texture, higher overrun integrity, and reduced air pocket separation. This is not theory. In Argentina, one dairy group implemented kinetic stabilization protocols across its regional delivery fleet. Within 6 months, they saw a 38% drop in post-delivery complaints, tied to texture and product inconsistency. For the customer, it was a better product. For the company, it was a quieter supply chain, less loss, fewer returns, more confidence in transit quality. Movement had been managed, not just the cold, but the choreography of motion, because in this domain, the road itself is part of the preservation equation. This reframes the entire cold chain. Refrigeration is no longer the only frontier. It's joined by motion control, by a recognition that the forces acting on frozen goods are not just thermal, but mechanical. Roads vibrate, loads shift, trailers flex, and unless those variables are absorbed, deflected, or neutralized, the cold alone cannot protect the cargo. It's a stark reminder. Cold is necessary, but insufficient. Because if your cargo moves like a rock in a blender, it doesn't matter how cold the environment is. Damage has already begun, and the consumer will only notice at the very last stage, when they open the lid, take a scoop, and feel that something is off. Not warmer, perhaps, but coarser, grainier, less alive. That change began hours earlier, not from thawing, but from vibration, from subtle shifts that triggered invisible collapse. In frozen logistics, silence is not the absence of damage. It's the space where damage hides. A scoop of ice cream seems simple, familiar, harmless. Yet it embodies one of the most advanced logistical processes in the food industry, one that blends thermal physics, mechanical engineering, sensor technology, and real-time data synchronization. Behind its softness lies an unyielding rigidity. Behind its sweetness, a world of constraints. Transporting ice cream is not a question of cooling. It's a discipline in preserving structure under pressure. A mission where both time and motion are adversaries, and where success is measured in molecular stability. When engineers and logistics operators handle ice cream, they don't think in flavors. They think in thresholds. Below a +20 at the Grex, its emulsion remains intact. Its air cells retain structure. Its sugar and fat molecules stay suspended in equilibrium. A deviation of even 2 degrees is not just a temperature fluctuation. It's a molecular breach. Ice crystals begin to grow, seeking paths of least resistance. In a few minutes, the ice cream becomes something else. Still frozen, still sealed, but no longer the same product. This need for precision is not unique to frozen desserts. It echoes the logic used in the transport of vaccines, where thermal variance must be kept within half a degree. It mirrors the calibration of industrial parts shipped across continents, where vibration must be neutralized to avoid microscopic stress fractures. In this ecosystem, the cargo may be edible, but the system is built like a laboratory. Agriculture offers an instructive metaphor. Think of the seed drill, one of the cornerstones of modern farming. It doesn't just scatter seeds. It meters them, calculates spacing, controls depth to the centimeter, even as it moves over uneven terrain at speed. Every variable matters, just as it does in cold chain logistics. Where the seed drill offers uniformity in growth, the reefer trailer offers uniformity in preservation. Where one deploys precision in planting life, the other applies it to sustaining quality. Both operate under the same principle. If you want consistent output, your inputs must be engineered with discipline. This mindset is already reshaping how global companies approach frozen freight. Between 2021 and 2023, Nestlé deployed a fleet of IoT-monitored refrigerated containers across Southeast Asia for its frozen dessert division. The goal wasn't just temperature tracking, it was predictive intervention. Internal sensors tracked ambient conditions, route topology, and refrigeration unit performance in real time. Any sign of deviation triggered dynamic route adjustments or alerts for preventative maintenance. The result was a dramatic 82% reduction in thermal excursions. Not because the containers got colder, but because the system got smarter. This evolution marks a new phase in cold chain logistics, what some now call intelligent thermal choreography. No longer a matter of moving boxes in a refrigerated environment, it has become an orchestration. Temperature sensors working in tandem with kinetic dampeners, route planners integrating weather forecasts with road vibration patterns, human decisions supplemented by algorithmic foresight. All with one purpose: to preserve what cannot be restored once lost. It's easy to underestimate the complexity. After all, the consumer doesn't see the process, they only taste the result. They open the lid, scoop the surface, and expect softness, smoothness, flavor. What they don't see are the counterweights under the pallets, the pressurized airflow systems in the docks, the phase change plates keeping temperatures steady inside the container. They don't hear the algorithms running silently in the background, calculating exposure risk by the second. And they shouldn't have to, because logistics, at its best, is invisible, not absent, just perfectly synchronized. And that's what makes this field extraordinary. It isn't about heroism, it's about control, about knowing that a product with a shelf life of weeks can survive a journey of days, across distances, climates, borders, without degrading by even a fraction. About designing a system where the fragility of the cargo is offset by the resilience of the process, where technology, far from replacing human care, amplifies it. Ice cream teaches us that in logistics, cold is not a destination, it's a moving target. And to hit that target again and again, across seasons and continents, requires more than insulation. It requires foresight, systems thinking, mechanical empathy, the kind of engineering that doesn't just keep things cold, it keeps them intact. And perhaps that's the greatest achievement of all, that in a world moved by mass production and relentless speed, there are still systems built for precision, for preservation, for excellence in motion, one scoop, one container, one perfectly preserved load at a time.